got this because someone is okay. So the problem was I looked at the problem for some few minutes, but yeah, let me just write it and then we see. So P is a polynomial in two variables, right? Or maybe since it's already using, so let's write UV and then uh, yeah, just a minute. Someone wants to join. Yeah, okay. So this is a polynomial in two variables, and the question is find all polynomials. Mahima, there is some background like noise. Is it? Just check it. Yeah, just check it. Yeah. Okay. Find all polynomials P such that. So I'll just write the question and then I will explain the context to whoever has joined new. Yeah, I think now it's okay. Such that this is equal to uh, yes. So xz minus yt and xt plus yz. Yeah. So yeah, before we discuss this, I have also not tried, but Arithria, so this is, we are just discussing this question. Okay. This question happens to be from what? ICM or IMC? IMC. Okay, right. So we're just starting to discuss this. We have not done anything. Yeah, so let us all try it. I think Mahima has tried it, so she can share her observations maybe first, and then I mean, okay, but yeah. So you're viewing P as a function from C to R. Yeah. Okay. So I'll okay. Yeah. Right. Okay. That's the analog, of course. Yeah. Yeah. I will not writing that because that's the only natural way to consider it. Okay. Oh, P of A. Oh, right. Is equal to P of right. Yeah. This is the this observation I made. Like so, there is no linear polynomial and so on. I observed that, but just give me a minute. Yeah, just give me a minute. This is something interesting. I mean, I didn't see it like this, so just a minute. Just- Okay, yeah. Yeah, go on. The reason why I did not consider this is because this will not be a differentiable function of C on C. Okay, that is there. But anyways, continue. That's probably not useful. P of zeros. Okay, yeah. All right, yeah. But but just a small question. Does this actually satisfy this equation? It does. Of course. Sorry. Yeah. Yeah. Okay. Hmm. Okay. So you are considering those two cases. Yes. Yes. I know. But I am just. I cannot. I'm just. I- thinking of the homomorphisms is like it's a complex homomorphism from C cross to R. I okay. Yeah. So I'm staring at it for that. Okay. Yes. P of one is zero and P of one is right. Okay. Okay. Yeah, sure. Yeah, that of course satisfies. Okay. Okay. Let me just because now we are focusing on a particular thing. P of zero is zero. P of one is one. Yeah, the reason why I'm getting a little confused is because this is actually not a. It is not a complex polynomial. You are just you're writing it like that, but it's actually not a complex polynomial, right? So because we are used to whenever we write like this, we used to thinking, okay, P is a complex polynomial, but this is not a complex polynomial. Okay. So your claim is that P of C is inside R cross. Oh, right, of course. Yeah, yeah. I think I will take it. That's not a problem for me. Aditya, I think is that fine because it's just a group homomorphism, so it will take C cross to R cross only. Then we'll skip it. There is, yeah. Right. So this one, we are not. Uh, oh, you okay? Okay. Yes. Okay. And so that's where I was wrong. I think I was wrong in saying that it's already a group homomorphism. We have to prove it. Means we don't know if C cross goes to R cross. But still, I think we can say it directly. But tell me, I mean, does this not imply that the image will be in R cross? Oh, right. Okay. Okay. Yeah. Then you tell us the proof. Yeah. So it's not directly following only from the algebra. Okay. Okay. Yeah. And then from there it follows, right? Yes, yes. So yeah, okay. I mean, yeah. So the point was that yeah, okay. Anyways, I'm just unnecessarily saying yeah, it's right. So it's okay. Then what happens? Yeah, yeah. Okay. No, that's fine. That's fine. Okay, let's check it though. So let's say P of Z is equal to 1. Then, so how do you show that Z mod Z is 1? Oh, okay. Then, yeah, then you say the steps. Mm-hmm. 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 Okay. Mm. Ah, right. Good. So it's 1. Yeah, so you are using that it is a quadratic, it has all the quadratic extensions. In fact, it has all algebraic extensions, but you're only using it as quadratic extensions. Okay. So, yeah, so far you have shown that P of S1 is in 1. I mean, right, yeah. So, yeah, I'll just say it. So, no, so it is because it has all the extensions, right? So, P of A, it is this, right? So P of Z is equal to P of Z1 square, right? So this is, so it means now this is a square. So this is P of Z1 square. And P of Z1 is also a real number. And so square of a real number cannot be minus 1. So it has to be 1. So this having extensions is forcing it to be. I mean, probably you can just say it's a continuous map, so the image will be connected, and so it's 1. Like, why do you have to? I mean, no, it's fine, but it's a continuous map, and so image cannot. Some points go to 1. You've shown that 1 goes to 1, so nothing can go to minus. You should, yeah, yeah, yeah. That's yeah, because if you go to some other topology, then maybe, but S1 will always remain connected. So, anyways, uh, okay. So this is 1. In fact, you have shown it is 1. Yes. I think, yeah, 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 yeah. Right. That also we have to say, but yeah. Yes, because the image will be a closure of 1, right? Correct. Yeah. Okay. P of A equals to P of R. Okay. Yeah. If I'm just writing it. Okay. Mhm. Yeah, it does. Right. Okay. So P of RS1. So this coset also goes to 1. Yes. Mm-hmm. Mm-hmm. Oh. No, but the R is fixed, right? So how does it go to 0? Oh, sorry. 1 by R. Ah, 1 by R. Okay. Okay. Yes. 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 Yeah. Right. Yes. Let's see that. So this is equal to 1 because of conjugate or whatever. No, not conjugate 1 by that. Yeah. Uh, because 1 by R is also in the kernel. I mean, meaning, yeah, yeah. So you're using this thing. Yeah, it's a mixture of two very strange things. Yeah, it's a that's why. But yeah, it's all correct. It's all correct, and so you raise it to the power n and you put the n inside, and okay. So everything is fine. So you just shown that the kernel is this compact subgroup S1. Okay. Okay. So I'll just write. Okay. Yeah, indeed. Yeah. Okay. Oh yeah, those are the only two elementary symmetric polynomials. You're in two variables. Okay. Okay. So P, how should I write it? P of x comma y is equal to, yeah, right. Yeah. G of x, y. Okay. Okay. Hmm. Right. So okay, yeah, norm meaning x comma y, x plus y, I y going to x square plus y square. Okay, that polynomial satisfies this identity, this one. Okay, I did not see it. uh, mm-hmm. Yeah, yeah, now I see it. So okay, the way I see it is, so p of x plus iy going to x plus iy is a solution. Like that's the very, because this is basically complex multiplication identity, right? If we forget the p, this is what we learned in high school, complex multiplication. And but then the set of polynomials which satisfy this also form a multiplicative set closed under conjugation. So z is there, so z conjugate will be there, so z times z conjugate is there, so z mod z square is there, which is what you're saying. Okay. Okay, so that's one function. Okay, so you have found the real function. Yeah, because I had, yeah, that's good. Okay. Hmm. Yes, because it's because a set of solutions of this, because that's what we do, right? In we look at all we look at the structure of the family of solutions. Then we can, yeah. Okay, so maybe I should just write directly. Yes, so basically everything arises from I, the complex number I. Right. We have to use these things maybe. Yes. So why don't we you think like this maybe? In fact, this is what we were discussing in the last class, that any continuous homomorphism from Z, so Eritrea was there, and this is a very standard result actually. Any uh, homomorphism of, oh no, uh, just a minute. Yeah, so any continuous homomorphism uh, of C cross would be, so certainly you see Z going to Z to the power n are there, are continuous homomorphisms from C cross to C cross. Sorry. Yeah, but this is slightly different, no? Okay. Yes, yes, I understand. Yeah, yeah. Then this is, then you can prove this. So try to use the fact. Try to use that fact. You don't have to use this. I think use the fact that, so basically you're saying that this is a radial function, kind of. So you're saying that it's constant on circles around the center at the origin, right? So it's a radial function. That's a very common concept in Fourier analysis. But let's see if we can use that. Yeah. So, and this is also suggesting that. So what you said is, I'll just assume it. So you're saying that, uh, how do I write it? You are saying that P of A is equal to P of B if norm A equals to norm B. Is what you said? No. But does that not mean this? That's the same. And this is the way, yeah. So this is the thing. Yeah. So this basically means that your function from C cross to R or R cross, this actually will become a function from the quotient C cross mod S1. Oh, I mean, you have also proved it here. So that's what you are saying here. And I am not, I thought you're saying something new in the sense that I did not see that you've already done the work. Right. And so the function factors from here. But then what is this function? This function is Z going to norm Z. Right. Z going to norm Z. Right. So basically this is, I mean, this is the thing. And so this is a radial function. Ah, yeah, because you see that's a natural function, right? From C cross to, is that, yeah, because, yes, you're right. But okay, how do I say it? Yeah, I mean, I can, okay, so you have done, quotient topology, right? Okay, so I can say it from there. One can say it more easily, but so the point is that you see, you check that this is a quotient map. Okay, so now this is a quotient map, and you look at the fibers of this map. Okay, now the fiber of this map, so you take a point here. Yes, yes, it's nothing. I just mean that take a point, take a real number in this. Okay, I mean, I'm identifying this with R, the group R greater than equal to 0. And I'm doing this map. Now it looks more in a better form. Now I'm saying that this is a quotient map. What I mean is that you know what a quotient map. So this is a quotient map. And now that's number one. Now you see that if you take any point Z naught, or rather now it is real, so I say R, and take the inverse image of this. Okay, calling this map P. Okay, that's already P is there. So I'm calling this map pi. Now if you look at pi inverse R, right? That is, so all of the pi inverse R maps to a single point here. Because that's a statement you actually just, same statement what you said. I'm not saying anything new. Then by the universal property of quotients, this map will factor through this dot dot dot. Okay, but this is a fancy way, but I mean, this is how we think. One can say it more easily, but this is what I want to say. And so basically, I think now we can say that, uh, let me just write it here. Maybe no, I'll write it in the same board. Yeah, now we can say that this P of Z is equal to Q of norm Z, right? That is Q is some other function. Yeah, which is basically that saying that P of x comma y is equal to Q of x square plus y square. So this much we get for free. And your functions, of course, satisfy these. But what do we do now? Okay, see, now you just study, because now you can now of course you know that this will also be a group homomorphism, because everything is a group homomorphism, so the quotient will also be a group home. Now you use group theory ka quotient, the first isomorphism theorem kind of thing. and there is a group homomorphism. And yeah, then you try to show that the group, now we come to the next board maybe, try to show that the group homomorphisms of this, yeah, and it's a continuous group homomorphism, so it maps to one connected component. This has two connected components, okay. Try to show that the group homomorphisms of this should be x going to x to the power n. That should not be difficult. But you see, we have already encoded that, I think, here. We have already used that. If you want to use it, whether you will use it again, I don't know. Like, you see that we have already used that. Now, if it's a more profound question, maybe you have to use it once again. I'm not saying, but probably no. You have to just check that the group homomorphisms of this is just this. Okay, that maybe I'll leave that. I mean, because you see, yeah, this is okay. I mean, this is nothing because what is this? I mean, this is isomorphic to R plus by the log or logarithmic or exponential, whatever, logarithmic probably. And then this becomes a good old Cauchy functional equation. Uh, I mean, this will become like a Cauchy functional equation, right? Like, so, no, no, okay, you know. So what I'm just saying is that no, no, I'll just write a thing, then you will know. I mean, you already know it. So you are just looking at solutions of this. And you would have proved in high school, right? That some x going to n x is the only solution or something like that. Or, yeah, yeah. So you see, so you have done this problem. Or probably I'm just rushing due to the excitement of the finish line, but yeah, that is probably clear. So, but I should. So you have done that if you have equations like this, then the only solution is, of course, under continuity, right? Because you prove it for rationals and then, so then you have this. I'm saying that you can do this in the same way because, you just take log. And why do you take log? Because you can assume that this maps into R positive or R negative then you, because it's connected and, continuous connected. Use everything that you know and you'll get it. Yeah. And everything, all of these things are coming down to saying that the one-dimensional representations of of S1, I mean, okay, that every, okay, that the one-dimensional representations of S1 are uh, the one-dimensional representations of S1 would be basically just C cross. That is the fact, means if you just frame it in the language of representations, then this you will get this. But I'm not defining it right. Okay. Everything is coming down to that. And in fact, this is what if you do in Galois theory also, right? If so at some point you would have proved that degree that the I mean, of course, you have proved at one point that the size of the Galois group is less than or equal to the degree of the extension. You would have used characters there or some functions and independence of characters and things like that. These are characters. Okay, in some form or the other, you would have done. Okay, so these are all same circle of ideas, fortunately. Unfortunately, because yeah, this is what you have been doing in some sense. Because see that what is this? This is a group, right? And this is the multiplicative, and this is the multiplicative subgroup of the field C, right? But if you generalize this to this, then these should remind you of the Galois group, elements of the Galois group to field automorphisms of K fixing something. The fixing is probably not featuring, but so those are generalizations of these things called characters. And the characters are all coming in this form is basically everything is boiling down to this Cauchy functional equation and using the compactness of S1, which implicitly we have used at one point because we have used that it's at least we have used that it is closed. and bounded. Actually, we used both of them, right? So that compactness actually forces some nicer things, which is what is implicit in all these things. Okay, but but still, I mean, all these steps you have done are require some thought. So definitely, yeah. Okay, differentiation in the beginning. Oh no, yeah. So in the beginning, in the beginning I said that I was misled actually into not considering this as a function from C, because when I thought about it as a function from C, it's not a holomorphic function. Complex analysis. Have you? Okay, so it's not a okay. So what I'm saying is that your solution set has this function z going to z conjugate, right? So x plus iy going to, or maybe I should say x comma y going to, uh, okay, I mean, yeah, okay, no, never mind, yeah. X comma y going to x plus iy. This was actually also one of the solutions, if you allow for complex solutions. Complex coefficient polynomial, this was also a solution, right? But we disallowed it because it was not. So when I saw this, if you look at this thing, um, this thing is fine, but then you see that x minus iy is also a solution, right? Now this function is not a differentiable function. If you think about differentiability, if you think about complex differentiability, okay, that when you do that, because it kind of reverses orientation, because if you see like the conjugate function, right? Z going to Z conjugate, Z to Z conjugate. You see that it reverses orientation, right? You move like this, but the conjugate function moves like this. So that's why it's in that sense it's a bad function. Okay, so it's not holomorphic. And so since I know since yeah, so whatever, then I did not consider it. But in fact, it was a nice thing to consider because of this thing, because it's still a group homomorphism and everything. Yeah. Anyways, so okay, that's fine. So let's just can I just take a 2 minutes break, and then we can look at that inverse Galois problem which you are saying. Yeah. Okay. Yes, it's quite a nice. This is quite a nice question. When has to be from IMC. Yeah. Hmm. Okay. Nice. So 1 minute. Okay, if you're in CMI, then second year, fourth semester, it is taught. Yes, yes, yes. Ah, okay, then you will be learning it soon, I think, right? Yeah, so that is fine. Yes, here, especially complex analysis, we did not use, is not used. But you see, this concept of quotient topology, suddenly it makes things, you can still say this without it. But for example, do you see a way to say it without this? Because it's a function of the radius, then yeah, actually, wait. So yeah, actually you can, because what you're saying here is P of A is equal to, if you write A as x comma y, then you're saying that P of uh yeah, yeah, you can say it. But this way it's kind of, it's easy to see it if you, yeah, if you know that language, it's easy to see. And yeah, okay. Let's move on. Yes. Yeah, so you tell me what you are saying, because I don't know that inverse Calvert thing. Okay, okay. Indeterminates. Right. So it's a, yeah, so it's a function field. Okay. Logical capital K. Okay. Yeah, this is everything. Yeah. Okay. EJ is equal to, okay. Just 1 second. So what is the Galois group of K over X small k? Yes, yeah. Yeah, that I agree. That is fine. Yeah, Sn is embedded inside this. Yeah, yeah, just 1 minute. Yeah, see, this is clear. Okay, fine, fine. Okay, then. Yes, yes. Mm-hmm. Yeah, yeah. F is irreducible over. Yes, yes. Okay, so you are going to say that K over KSN has Galois group Sn. Yeah, yeah. That result is elementary. Yeah, I understand. You will say elementary symmetric functions are transcendental and something like that, right? That is not inverse Galois theory. I mean, that is easy, right? I mean, you have a huge extension, you are finding your convenient sub extension, and you're saying, I'm interested in fixing K and finding an extension. Yeah. So you have proved that K over KSN is Galois. Of course, it is Galois because you have taken it like that, fixed field of something. So gal of this is Sn. This because I have seen this, Arithra, if you can just prove it later. So if you have not, otherwise it's fine. This is an exercise. But well, of course, as we know that I'm interested in, and also, uh, sorry, probably I am again asking the same question. Have you or does anyone know what is what is this Galois group? I know it might be infinite, but is there a is there something that we can say about this? Uh, or is it, I don't know, is it K cross? Is it K cross? That would be a question. Is it K cross or something? The field K, it's small. I don't know, or something like that. Some field constraint. Because see, it's not going to be one of those if you have done profinite groups. Uh, if I'm, it's fine if I'm not. Yeah, profinite is sort of a limit of inverse. So limit of finite groups. Finite. So how? What do you say? Well, give us some good example. The problem is that I should know, but I don't. Yeah, like this right. This is kind of a profinite group. The closure, the algebraic closure of no. What do you say? Do you say algebraic closure of Q? Yeah, right. This is going to be, I think, a profinite group. Please correct me if if someone knows. This is a profinite group, and profinite group. The idea is that it is a limit of finite groups. Okay, and these groups are very important. Even like recently, papers are being written where they are talking about these things. Yes, that that is one case will be that. Yes, yes, one case will be that. But it could also have like inverse limits and so on. For example, if you have done p-adic integers, yeah, so you will do that soon, and we will see because they are good examples of locally compact. Okay, let me just say. So what you do is you look at this. And I will not guarantee. I will ask you to check if it's a limit, but I will give a analytic description. I'll do it like an analysis person. Okay, and then let's see if we can find a algebraic variation of it. So I will look at Z. I will put a metric on Z. Please, I think Aditya, you would know this, so just correct me if I'm saying something wrong here. I Because I don't know this very. Oh, sorry. Uh, Probably some connection error, connection problem. I don't know. Anyways, okay, let's continue. So, okay, no problem. So you look at this. Okay, I'm putting this metric. What is this metric? So, as you can probably guess, so I will say something like p to the power n. This is 1 by p to the power n. Sorry, there is no minus. Okay. And then I will say something like 8 or maybe, okay, in general, n, the norm is, I'm putting a norm, okay, and this norm will be 1 by p to the power order of p in n. Okay, so I'm putting this norm. So as you can check that this is a norm and so on. So with this norm, you look at the integers. Okay, now it's a metric space because there is a norm. Take its Cauchy completion. Just take the completion of that metric space. Okay, uh, maybe you have to review this completion of a metric space. Take the Cauchy completion of this. Look at what that is. Okay, and the claim is sort of that it can be described as a limit of, I hope I'm correct, of z piece, some sort of a limit of z piece. Like you have to take infinitely many copies of z piece and you have to take a limit in some sense. Because the Cauchy sequences you consider will be the elements of the completion. You have to think. So these are examples of profinite groups. So this can be, uh, yeah, can be useful. Okay. Yes. 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 Yeah. 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 Maybe. Yeah. So okay. Now the main question which you asked me the last day, which is still unsolved, is as you said, right? So you find an extension of Q. Find an extension of Q. Yeah, finite extension of Q, such that gal K over Q is Sn. This I'm not able to do. I know the answer is yes. There is some because we did it in our Galois theory course. But yes, and I even made some small observations, which is standard one actually. Yeah, but yeah, my claim is, and of course it's built on the first result that day, that there is a polynomial which is whose splitting field is k. Right? Sorry, not just that, an n degree polynomial. Because that's the result you proved, right? If such a thing exists, then you can find a polynomial which does an n degree polynomial. And my claim is that you can do it. My claim is that f has real roots. I mean, not like that. Like f can be found so that it has real roots. There exists f with real roots, such that yeah, splitting field of. But I'm not able to find it. I was trying it today also a little bit, but I couldn't do it. This is the problem. Not able to do this. This you see is a little harder question, right? Because this is not just Galois theory anymore. You need some, it's not just abstract result. Okay, you take this extension, take this fixed field, and this comes out. No. Some, yes, I at least, yeah, one of the proofs which I vaguely, because I recall seeing a proof, but I don't want to just look it up. I want to try it, or I want you to try it. Okay. Yeah, why don't you try like degree 4, degree 5, do some calculations, hard calculations, and see. Right? That might be how, yeah, how do you, yeah, I don't know. I don't think so, but yeah, yes. So you have to just find a polynomial and show that all the transpositions are there somehow. But how to do it, I don't. Maybe 4 degree if fx is. And I think general inverse Galois theory questions would be what subgroups can you get in this way? because it's you won't get every subgroup. Even though you get SN, I don't think you will get every subgroup. Over Q, if you want it over Q. Otherwise, of course, you will get. Okay, how? Yes, yes, that is fine. Yes. Yeah. Uh, uh, hmm. Yes, but that will not no more. But now the extension will no more be over Q. That is the problem. Yeah. But I mean, you are right. I mean, you can get quotients. You can get quotients of SN, all quotients of SN. Yeah. But yeah, so that's one class of groups which you can get. But everything is not a quotient of SN. As we know that because often you have to quotient free groups to get your groups. No, like no, I'm saying that like if you want dihedral group on two letters, do you get it by SN? No, you have to take two free variables. You kind of I'm saying that you have to take two variables without any relations, and then you have to quotient them by some relations, right? So the group which you're quotienting or initial group is what is called a free group, meaning that there are no relations. They are just words in two letters, right? So that kind of thing. So SN is usually not good if you want to quotient. Uh, yeah. Anyways, let's see. At least for four, if we can work out some analysis might be needed. Some roots, something. Hmm. No, I don't. That's the thing. I don't think because there it's sort of you only use algebra, right? Because we are only using the structure of, but now is roots which have to come. There sort of it works out due to just sort of elimination. There is a element of order two, so you get S3. But you see, if you prove that you have elements of all order, then it doesn't necessarily mean you will get Sn. So if you have a subgroup, because this will be a subgroup of Sn that we know, but if a subgroup of Sn comes, yeah, because p factorial you will get Sp. Sorry, I mean, if p is prime, you can prove it, I suppose, maybe. Because if you prove that you have subgroups of all order, then you will get, because p factorial is a special case. P is special. But for general n, it's difficult, I think. And yeah, I don't even then know if it is true. I think it is true now, but let's see. Should be S4. Huh. Uh, yeah, sure. Yes, that's correct, I think. Yeah, yeah, that's the case. Mm-hmm. Yes. It. And but I don't know how semi-direct products interact with field extensions. There would be some interaction, but I don't know. Maybe some operation on field extensions will give you semi-direct products. But then I don't also know if it's easy to find AN as a subgroup. Or if it is even possible. I don't know. Yeah. think about it maybe. Yeah, I'll also think about it. I think it's worth to think and try, because then maybe we can come up with some ideas which is original to you or original to the little bit of a research, right? Even though it solved problem and so on, but it will be your original. Uh, yeah, try it maybe. Yeah, then maybe next week you can tell me. I'm sure if you try it, you will get. You spend a few hours maybe. Yeah. Let's see. I don't know. Yeah, I think because these problems are the problem is that these problems are more systematic still, right? I mean, it was a general, but here I don't know what. Okay. Anyways, think about it. Okay. Then let's meet. Let's meet next week. Yeah. Huh. Okay. Yeah, but what time? Yeah, the problem is that usually I prefer mornings, but that will not work for you, right? Yeah. Because after that I have my classes, no, college classes. And then after coming back, I will usually not, yeah, it will be late and so on. Yeah. Yes. So, uh, yeah, I think that will not work for you. So, but yeah, maybe like one day, so maybe Tuesday, 8:30 p.m. Monday, no, because Monday I have some other one seminar to attend usually. 8:30 p.m. So maybe there will be some other people also in that one. So because yeah, because their college is also opening, so they're also requesting for the evening class. Yeah, yeah. So for 1 week we can do like that, and then again on Sunday we can do. That is fine. Yeah, actually, it's so there also the plan is to discuss Galois theory. Yeah, yeah. So actually, the plan was to do solve some problems of Patrick Morandi. So there's a Galois theory book, and just to solve, I just started Galois theory somehow because some other person also needed for their project. Yeah, so we are going to do that. But yeah, it could be quite wild. I mean, it could be it's very unplanned. Yeah, in the sense that I don't plan what I'm going to do, because that's not good for this kind of class, I feel. Yeah, but usually it will be slower because people won't be as comfortable with everything. Yeah, that is the thing. Yeah. Okay. Yeah, but it will be fun. I mean, you'll get some new things and you try it there. That will be nice, because that is needed. Because this is something which you have thought, so it's fine. You told me, it's nice, obviously. But someone gives you a new problem and you solve it there, even if it's slightly easier, it's a bit challenging, and it's nice just to keep things. Yeah, because some question could come from differential equation. Someone has some question. They will all be from this MSc or PhD entrance exams. So it will be nice. Yeah, but they're not. Yeah, some post graduation or undergraduate, and they're preparing for the next thing. So in India, like we have to write the entrance exam. So the questions are not that long and like this one, but they are very varied. So you could get some. Yeah. So I like that, because that way it's nice. Because I mean, otherwise I'm doing theoretical stuff all day or whatever. I'm doing theory. Yeah. So it's good to get new kind of questions, even if they are easier. Yeah. You can say it's miscellaneous. Yes. 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 Yeah. Okay. So yes. Yes. Yeah. Okay. Then Tuesday, 8:30 p.m. Okay. But I still, if there's a change, I'll tell you. Okay. So that there's no miscommunication. Also, do you have your exams? You have your exams or something? Ah. Okay. Okay. That's fine. Okay then.